So, good afternoon, one and all. Today we have the privilege to have Professor Indranil Malna, Honorable Vice Chancellor from Birla Institute of Technology, Mesra, Ranchi. Sir, may I request you to take your designated seat on the dais, along with our Honorable Convener, Institute Seminar and Outreach Committee, Professor Raghunath Sahu. Sir, please. Thank you, sir. So, as per the Institute tradition, may I request Convener Institute Outreach and Seminar Committee to welcome Professor Manna with a bouquet of flowers for sparing his valuable time for IIT Indore. Thank you, sir. And just to take the session forward, may I now request our convener for formal welcome address and also introducing the eminent speaker of the day. Sir, please.
So good afternoon to all of you. We are extremely sorry for the late which happened because of many associated reasons. Although we tried to pick up with time, but there is a delay, so please excuse us for that. And let me start the program. So as truly mentioned by Professor Manna, if science is know why and engineering is know how, then the technology is know what. So connecting science and technology to society has been a major challenge for any scientific endeavor. And this starts with encouraging our own ambassadors, the students and the faculty community of IIT Indore. In this direction, IIT Indore's initiative of the public lecture series BIMMERS starts today with the first lecture with the august presence of its first speaker, Professor Indranil Manna. And it is a true pleasure and privilege for me as the convener of the Institute Seminars and Outreach Committee to welcome you all to BIMMERS IIT Indore Public Lectures, and a special welcome to Professor Manna on on behalf of IIT Indore fraternity and also on behalf of Director Professor Joshi. So unfortunately, Professor Joshi, our director, has to chair the Senate meeting, which is running parallelly. So Professor Manna is going to illuminate and recharge our audience with the chosen topic of today, which is science, engineering, technology, synergy needed for technological self-reliance. And as you know, this is a topic that is highly prudent at the present time when we gear up as a country for self-reliance. And the role of science and technology will be of great importance. It cannot be ignored when you go for self-reliance. So I must mention here, IIT Indore has taken some important initiatives recently to connect academia to industry in one direction and to science and technology to industry readiness level. On the other hand, IIT Indore has also taken initiatives in identifying the problems of a rural sector, tribal people where technology can be of help to ease the issues. IIT Indore has been trying to cover the whole spectrum of the society to bring science and technology for the benefit of the global well-being. And so I take the privilege of introducing our esteemed speaker of this first BIMMERS lecture series, Professor Manna. He is presently the Vice Chancellor of Birla Institute of Technology, Mesra, Ranchi, and he is an educationist and materials engineer with wide-ranging research interests covering structure property, correlation, and modeling in nanometric metals, ceramics, laser plasma assisted surface engineering, nanofluid, etc. He has been teaching in IIT Kharagpur since 1985. He worked as a guest scientist in different renowned institutions and universities across the globe. You may be knowing because you are attending this Dhara program already. So starting from Max Planck Institute to the University of Ulm. So Professor Manna has over 260 journal publications. He has supervised 25 PhD students, and he has completed externally funded projects up to 30 crores at IIT Kharagpur. Received several awards, including the Third World Academy of Sciences Prize for Engineering, Humboldt Dad Fellowship, GD Birla Gold Medal of IIM. I'm making explicit mention of this because we have the next generation. I believe that they will be encouraged with the academic profile of Professor Manna. So that is the point of mentioning here. And he has also received Platinum Jubilee Medal of ISCA, INSA Young Scientist Award, Young or Best National Metallurgist Award for the Ministry of Steel. He was the INAE Distinguished Industry Professor, President of Materials Science Section of Indian Science Congress, INAE Visheshraya Chair Professor. He is also fellow of all 4 academies in India and also the Third World Academy, Asia Pacific Academy of Materials. He received DSc honoris causa from Kalyani Kaji Nazrul University and Distinguished Alumnus Award from Sivpur, the famous engineering college, and IIT Kharagpur also. So earlier he served as the director of IIT Kanpur. When personally I came to know Professor Manna, even if I am from physics, and CSIR lab in Kolkata. And before I invite Professor Manna for this public lecture, let me make a special mention that we have taken the opportunity of this Dhara program, which MEMS is conducting. So I should congratulate all the organizers, including the head MEMS, Professor Vinod Kumar. So giving us the opportunity to have Professor Manna as the special guest, and we are starting this series. So it is a different movement for all of us. So we have named the series and we are starting with the first lecture of Professor Manna. At the public lecture, and we will not interrupt in between, and we'll take up the questions towards the end. Yeah.
So thank you very much, Professor Sahu. For being very generous. And to my young friends, you are to, I don't know whether you are allowed to have lunch or not, or Vinod probably drove you away from the lunch venue. But this is not my way of thinking, at least this much I should tell you. I didn't plan that way, but I'm very glad that we have a lot of young faces. And let me also mention upfront that this various places in various parts of the country. I'm personally very, very passionate about it. And I honestly believe that this is a philosophy which needs to be understood and practiced very seriously throughout the country, particularly in the engineering community. For reasons which are very closely related to ambition being self-reliant, Atmanirbhar. So also I'm deeply honored. I must express my very sincere gratitude to IIT Indore, the director, though he's not physically present here, but yesterday evening he spent a lot of time with me and explained to me what his whole initiative is all about. And to be the first speaker in this series certainly makes me feel very important. So let me start straight away. So can you change the screen? So I'm overshooting the time. It's now 3:30. Maybe take about 40 minutes. So by half an hour, after half an hour, give me a. So essentially, many of us tend to treat the three most important pillars of the progress of any country as disparate objects or disparate objects: science, engineering, and technology. The non-between actually should have been a reversible science. Reversible science is because they actually all are interrelated, and they not only interrelated, they actually implement each other. So The focus is how do we see a seamless translation of knowledge to prototype and eventually to a product, which accrues large-scale societal benefit. Okay. Then, so essentially, what I mean is that what do you do with knowledge? Unless it really provides some tangible benefit to the stakeholders, is it really of any major use? And a knowledge not necessarily always should produce a product. A knowledge should certainly lead to certain benefits somewhere. Some set of people, even if it is for pure scientific pursuits, should really benefit from this. Now, I would first draw your attention to the genesis of these institutes of technology. In the morning, I made a mention. We all, for example, IIT Indore, I belong to Birla Institute of Technology and Indian Institute of Technology, Kharagpur. Why did the forefathers, the planners for the nation before independence, why did they think of creating a new set of institutions called IITs, Indian Institutes of Technology? Already there's a list of 10 institutions, all of them are pre-independence, right? And you see all of them are very eminent. The first one is 1794, can you imagine? College of Engineering, Guindy. Then Roorkee, the precursor of current IIT Roorkee, the University of Roorkee, then College of Engineering, Pune, Bengal Engineering College, Shibpur, University of Bombay, VJTI, Jadavpur University, even IISc Bangalore. They all existed and they had a very flourishing engineering program as departments in many of them. But the Sarkar Commission, which was constituted before independence in 1945, proposed that there should be a separate set of institutions designed after the very famous Massachusetts Institute of Technology, MIT, and should pursue engineering with a very different focus altogether. And that's the reason why the vision statement of IITs, in fact, if any one of you ever get an opportunity to read that document, it's not a very lengthy document, very short document. And you realize, you really wonder that what kind of a vision these authors of this document had at that point of time. IITs never said that you should produce so many publications, so many PhDs, so many engineering graduates should have these many departments, you should produce so many products or something. Never said that. It said basically in the vision statement, the basic function of IITs is production of scientists and engineers, not technologists, scientists and engineers of the highest caliber. Goals and tasks of the institute should relate continuously to changes taking place in the socio-economic development of the country and rapidly exploding universe of knowledge in science and technology. Might sound very generic, but actually is extremely focused. The best quality of human mind should be produced in these institutions who should pursue science and technology. Now, knowledge is what is aimed at. And knowledge, if it's one coin, like any other coin, it will have two sides. And one side is teaching, dissemination. There is a textbook, there are literature available, there are experiences documented elsewhere. So you are very knowledgeable in a subject domain, and then you teach in the classroom. You actually expound a theory, you explain, you make all the students conversant with that. So that's teaching. But the other side of the coin is creation, research. So why did I say same coin, two sides? Because they complement into each other. Otherwise, I'll be teaching what I'm teaching today. Even after 100 years, I'll be teaching the same thing. So there's no growth. But with time, things evolve. And with evolution of knowledge, the various, the quality of life changes. Otherwise, we would be driving the same old ambassador car forever. Today, we are in a very different era altogether. Or for example, we would have had only bullock carts and no automobiles. So who feeds in that? That is because of our intent desire to come up with new and newer knowledge. So that's why these set of institutions were planned. Where did we begin? Today we were talking about a big time scale, almost 7,000 years, starting from the Paleolithic period all the way up to the recent era. So we are talking about a time span of nearly 7,000 years, 7 millennium. So there are two personalities which every Indian would immediately be able to identify. One of them said, education is the manifestation of perfection already in man. But I'm more actually inspired by the second part of the statement. Character is the test of that. How you behave, how you interact, how you present yourself, and how you perform is the test of your character. How do you derive your character? Through your education. Now, what is education? Education is imparting a set of knowledge. So you are getting trained in certain traits. And knowledge is awareness which evolves through time and stages of learning. I learn, I know, I'm aware, I'm capable of something today. So I get a degree called bachelor's. Tomorrow I go to higher level, I get a degree of master's. I go even deeper vertically. I acquire a doctoral degree. So basically in stages of learning, which is evolving with time, the set of knowledge which can give you a doctoral degree today will not fetch you another degree after maybe 20 years or 10 years, because by then that is already known. So you have to evolve with time. But then what Tagore said was also very interesting. He said the highest form of education, he's not saying which produces so many publications and create a four-wheeler or a flying machine or something. He's saying makes our life in harmony with all existence. Existence is changing with time, but the highest form of education is what will make you very much conversant and at peace, at ease with the change. So these two are very important, but then why I chose to pick up this particular view graph here is because this is how pursuing knowledge started in this country under the banyan tree. The guru is talking to the disciples and explaining certain theories, and peacefully they are trying to absorb what is being taught. So maybe a particular shloka, and it's just like a classical music. The same classical music rendered by three different gurus will appear to be not precisely the same. So that's why you need experts to explain the concept behind that. So the guru explains and the disciples try to absorb that. They raise questions, very hard, very insightful questions, probing questions, and the guru answers. And this kind of a discourse of constant interaction is what is needed for developing knowledge. And that's why you need a classroom, you need a teacher. The teacher is a teacher not because he or she is only very superior to you because of the body of knowledge. A teacher is a teacher factually because he or she was born before you and has gone through a certain level of understanding and learning before you and has attained a certain level by virtue of which one is able to explain certain facts and figures before you. Examples of knowledgeable ones in this country. And again, over a very large time span, maybe about 2,000 years or more. Today, in the morning, I started talking about interaction among atoms to make an aggregate and talked about bonding. So this basically was first mooted by someone from this very land. Rishi Kanad spoke about Paramanu. That's what our literatures claim, that the word Paramanu came from Kanad. So the concept of atoms and the smallest building block of solids and atomic aggregate and interactions among atoms was perceived by the scholars of that era. today we live more or less in a world of binary. Now, the very decimal system through which such advancement was possible is largely credited to Aryabhatta and Pingala and some of the scholars of that era. So that was the level of attainment of knowledge in this very land, maybe 2,500 years ago. But then I'm not tracing the entire history. Let's fast forward and come into the recent times. The period between 1861 until 1941, these 40 years, is an enigma. I've always wondered, and I'm sure many others also would do the same thing, in that 80 years, this country saw the birth of absolute legends who were all pioneers in their own field, and not just science, be it philosophy, be it religion, be it any walk of life. We had social reformers. We had plenty of these examples. But talking about science, imagine these four, or five of them: J.C. Bose, C.V. Raman, Ramanujan, S.N. Bose. I'll stop here for a while. Imagine all four of them had a period of overlap and in the same city and in close proximity. One who was employed by the Auditor General's office as someone who does accounting, in the leisure time in the evening, manages to go to a laboratory which was given as a goodwill gesture by a philanthropist, so that that person can go and perform some experiments. Eventually comes up with a completely new theory, not until then not even understood by anyone at all, and eventually goes on to receive not only the very first, the only Nobel Prize in Physics from this country, Sir C.V. Raman. Satyam Bose, many people still believe and argue that should have been given the Nobel Prize, and none other than Einstein, and today the most fundamental particle of the entire condensed matter is named after him. Unless someone has made that level of contribution, the Western world would never accept it. So similarly, Ramanujan is truly an outstanding mind. Even today, we don't know how many of his theorems are yet to be understood. Somewhere at the back of a paper, he wrote something and he probably threw it away. Maybe that is a treasure which has so much of knowledge in that. Then I've missed out one personality which I should have included is Meghnad Saha. Again, another person who many people believe actually is not only was a pioneer in cosmology, but actually his equation, Saha equation, was one of the major tools to go into deep space exploration and so on. P.C. Ray, in my opinion, I have another slide I'll share with you, is a role model before us. Why, I'll explain to you a little later. And Vishweshwara is sort of an icon before any engineer because during his lifetime, the number of national level interventions he made certainly makes someone feel very envious. Now, I was saying in the beginning that science, engineering, technology, we tend to say that you carry a degree BSc and MSc, he carries a degree BTech and MTech, and he's CEO of a company. So these are three different people. They have nothing to do with each other. And more so, if you are considered a scientist, you cannot be an engineer. If you're an engineer, how can you do science? And either of you, technology is to be driven by the technologists. Now, nobody actually knows whether an apple actually fell on the head of Einstein. Nobody has seen that. This cartoon is everywhere. Why? This is just to impress upon the important point that he was the first one who raised a very persistent and a fundamental question as to why apple should only fall and not go up. Today, we send satellites to the orbits, we send humankind to explore Moon or Mars or whatever, and we set many Even we talk of Star Wars or something and so on and so forth. Every time we talk of defying the gravity, how do you defy something unless you have defined it? So this was the laws of gravity that Newton came up with, which nobody understood would be ever useful or not. He was very true in his approach. He asked only one question, why? So science is all about that simple thing, know why. You don't care whether it's going to be useful today or tomorrow or day after. You don't even worry about that at all. But you are only worried about one fundamental thing, that you are going to come up with answer to something which is not yet known. You discover something new. Why? The second part is what to do with it. So there are a set of people who understands that, who looks around in the nature and says that birds can fly. Why can I not? So sets an ambition. I should be able to fly like a bird. And Da Vinci, though he is a painter, he's also a thinker. So he draws something, and this sketch, this is not quite working. The sketch on the top is one of the first few drawings available for a flying machine. 400 years mankind had to wait from the time Da Vinci drew that sketch. Till in early 20th century, the Wright brothers came together and actually managed to fly an object about 15-20 minutes, or maybe even less. First example of a flying machine. Today, you fly from Delhi to New York, Delhi to Melbourne in flat 12 hours, 13 hours, without even stopping. And this has happened within a span of 100 years. So this is the power of how to take care of, how to utilize the fundamental knowledge and then make certain useful implements. So know how. And then, but that was from what was possible was shown as a one-off example. And to make it commercial, you actually make it reach out to the large masses, large number of people. And for common societal benefit, you actually have to go one step forward, which is know what sells in the market. Say today, if you create a device, let's say a small device which can produce light. There are many torches available. You produce a light-emitting device which costs 100 rupees, and you can easily buy from the local market a similar thing or even better at say 10 rupees or 30 rupees. You'd never go for that other one. So you have understood the fundamentals, you know why, you have learned how to convert that into an implement, know how. Still it is not successful, or it's not going to help you until and unless you are able to take it to the marketplace and make it available to the entire masses, and that is technology. So we seem to believe that science leads to engineering and engineering leads to technology. So this is the one-way traffic. No. Einstein predicted gravitational wave in 1916. Was never proven, and scientists don't believe unless it's proven, right? I mean, you may have a lot of conjecture, you have a lot of philosophies, theories, but unless you prove it, nobody will believe you. It took exactly 100 years to have the Laser Interferometer Gravitational Wave Observatory, LIGO, established in 2 different places in the world, carry out exact experiments. For a fleeting second, they could detect the existence of gravitational wave. What made it possible? Technology. So it's not one-way traffic. They actually all complement each other. In metallurgy, we often refer to a phenomenon called age hardening. Aluminum alloys I was talking about in the morning is so novel because this is one set of alloys which, if you do certain thermal treatment, develops some precipitates in solid state, which gives it very good strength. So at low density, you get very high strength, which you can retain and makes it very, very useful. Now, this was proven by experiments that it raises its strength if you do such treatment. In 1929-30, by two individuals separately, Greene and Preston. So we call them GP zones, Greene-Preston zones. Existence of coherent precipitates were proven only in 50s and 60s by the advent of electron microscope. So 40 years, 30 years, people had to wait to get the evidence. But already people were using age-hardenable aluminum alloys. There were companies. But technology, electron microscope, actually proved the science was correct. So both are very, very important. So then let's try and understand the interrelationship. So science, in very simple words, as I said, is simply know why. In any natural phenomenon, in any observation, any occurrence, if you get an answer to the fundamental question as to why something is happening in one way or not the other, then you have the science, and usually it's a curiosity or need-driven act and leads to occasional discovery. So it's something like you have a grand XY plot. Suddenly, once in a while, in few decades, you get a large peak. That's discovery. Here you go to know how. What do you do with that knowledge? So can you make some good implements out of this? So for example, when Faraday showed that you apply potential difference, electrons flow. So be it, electrons flow from high to lower potential. What is the use of that? So you require somebody to actually show that if it passes through certain wires of given resistivity, it can glow, produce light. It can rotate a fan, or it can allow certain wheels to rotate. So you can make use of the electricity in different possible ways. So that's the translation part. That's engineering. But then showing just one bulb here or one fan there is not going to help. So you have to have companies, or you have to have individuals who can take it to the masses. So that's why we go to the technology which is know what sells. Multiple copies, and usually innovation driven. I was talking to one of the colleagues here. In many cases, the engineering exploits reach the market and survive by way of innovation. You would have very well known that, for example, the major electronic companies or IT companies will look around, scout for patents. In a given subject domain, let's say there are 100 patents filed in a given year. The topmost company will try to buy all hundreds of them. Why? Because of two reasons. Number one, they really are looking at whether there's some new innovation coming which actually can improve the quality of their product. But they also would not like somebody else to compete with them with such new innovation. So that's the power of innovation. And innovation is incremental, not a large peak. The large peak is discovery. And maybe a similar exercise could be an invention. But innovation always leads to certain exploits and certain incremental advancements. So this is the synergy of science, engineering, technology. And why does it happen that way? It happens that way because the modern knowledge ecosystem or the modern innovation ecosystem is entirely knowledge driven. So the academia produces new knowledge. The research organizations accepts that and creates an invention out of that, feeds to the industry, industry comes up with a viable technology. And moment you have a viable technology, it immediately goes to the market, the society consumes. You carry a cell phone today, you tend to believe that this is top of the shelf. I purchase it for so many thousands of rupees, and you feel very good that I have the best of the devices available today. So your joy will be very short-lived because within 6 months, you'll see version 4, version 4.1, then 4.2. What does it mean? Little incremental improvement somewhere, little innovation here and there will make the product perform a little better, more efficient, and so on and so forth. So immediately there will be a new launch and the companies will make sure that nobody uses the previous version. So this whole thing is actually a perpetual cycle because all the time the society is demanding better, cheaper, faster, easier, lighter, and all kinds of attributes, right? So this is the power. And in this cycle, now I hope I am able to explain to you that everybody has a role, the scientists, the engineers, the technologists, and so on. In fact, I go one step forward and I claim that same I could be scientist in the morning, engineer in the afternoon, and technologist in the evening, or vice versa. Because when I'm pursuing the fundamental question why I'm scientist, when I'm trying to translate how I'm an engineer, and if by chance I'm able to really do something spectacular which reaches the market, which of course is a very, very low fraction, then I'm a technologist. So if you're pursuing the fundamental path, you can be a Niels Bohr. Though his discovery eventually was proven wrong, but he laid the foundation of atomic structure, the planetary model of the atoms, right? We all know by now that unless it is atomic number 1 or 2 or something, the orbits are rarely spherically symmetrical. But nevertheless, that electrons are at a distance from the core, rotating at a certain speed, and centripetal and centrifugal balance each other. These fundamental concepts came from Niels Bohr. On the other hand, Edison didn't do any fundamental science. Edison simply looked at the theory proposed by the likes of Faraday, Volta, and so on, and he saw that, oh, fine, if this is how you can produce electricity, I can make use of that. So he lit the incandescent bulb. He created many, probably, I don't know whether he's still the holder of the record, but at some point of time, he was the record patent holder, like record number of patents he created, right? So that's entirely on the translational path. Very rarely we see the combination that Louis Pasteur showed. Not only he discovered, he actually created the first antibiotic. And today the whole world is safe against bacteria because of his discovery, invention, and even translation. Here is the Indian example of that. And I personally believe he's one of the finest of the examples in that particular category, the likes of Louis Pasteur. Mercurius nitrite, somewhat like Alfred Nobel. He created this compound which didn't exist. There was no record of the existence of mercurius nitrite. He could synthesize and prove the existence and derive the properties, and which had certain value, chemical value of certain energy and explosion value. And using that, he actually, if you look at his profile, he was the first professor of chemistry in Science College. You know, those days, Calcutta University Science College was outstanding because of the British influence. To be selected as the Palit professor was a huge honor, and he was the first Palit professor. 107 publications in 1920, all reviewed publications, was outstanding record those days. And then he had scores of students and so on. And he was the president of Indian Science Congress for a period. And yet he founded Bengal Chemicals and Pharmaceuticals, India's first company created by a discovery in India by a native during the British period. Bengal Chemicals was so rich that in Calcutta they had multiple places. I'm glad to actually share with you that Bengal Chemicals was totally in the red, was about to be closed down, but recently they have gone through a certain exercise and they still survive. But much of PC Ray's original plants all were sold to the real estate people. You know, that was the fate. But nevertheless, if any one of us sitting here can ever create a company which is valued a large sum of money and can create jobs for hundreds or several hundreds, we'll all feel very blessed. So that was PCD. About, we always say that decades of innovation or something. So this particular book chronicled the major innovations happened in the 20th century. And if you look at the list of these 20, you cannot think of life without them. And you also will be ready to agree that a century before, none of these existed. So they changed the face of the humanity over a period of time and within one particular century, right? So considering this, then all these are basically through the power of innovation, right? And when innovation happens, it's like somebody shows that this machine, if you design in a different way, or this sensor, if you use a different compound, or in this particular implant, if you, for example, make the curvature a little different, in a little bit of these interventions, the efficiency, the proficiency, the functionality is vastly different and more beneficial, is advanced. So each one of them actually is a huge possibility. And most of us in academia tend to believe that I have created a technology. I had the opportunity of serving in CSR for 3 years. And one thing that I learned while being in CSR is that there's a difference between technique and technology. Whatever you do in 2-dimension can very well be, can at best be a technique. If you do this, efficiency increases. If you do that, the permeability increases or the conductivity increases or something of that sort. You patent it because you have proven it as a prototype, okay? Still, it's not a 3-dimensional product. A 3-dimensional product actually is such a device or a sensor or a machine which actually proves that. So these things don't happen because of this so-called valley of death. The valley of death is that you have an idea, you show it, you prove it. You prove it before the learned community. But when you actually want to translate into a product, then you have to go through very many things, and it's not just one valley, there are multiple valleys. So just like one potential difference is not one single, it has a multiple differentials in between. So we need to bridge this gap. And if you just do a simple statistics, if 100 patents are filed and granted, not even 5 of them will see the light of application. This is a proven statistics. Why is it so? Because not all are, otherwise, things would have been so easy. It is not. So, taking cue from the previous exercises, United States decided to create a committee with to be chaired by, look at the power of their intention. William Perry was the Secretary of State, something like Home Minister, chairing a committee with experts, 50 subject domain experts, including some Indians, from 40 different countries. And they were tasked only one thing: predict what's going to happen in the next century. What will change the face of the humanity in the next century? And they made these kind of 14 very specific predictions, okay? And United States National Science Foundation gave it to National Academy of Engineering, and they launched a nationwide campaign, and they roped in all top countries in the world: Japan, Germany, UK, even China, and so on and so forth. And at that point of time, they also, I had the opportunity of actually leading a delegation to United States, and the president of NAE, he was very keen that India should also join, and we all deliberated. We came back, and there's a history that I wanted to share for 1 minute here. 2014, the then education minister invited all directors of IITs to go for a retreat. And she said one single thing, that you have to come up with some new ideas. So for 2 days, all bills paid, you are staying in this hotel, but not going anywhere. You just talk to each other. We got divided ourselves into 4 or 5 committees, and so we came up with certain ideas. And actually that deliberation continued for some more time, and by the end of the year 2014, around say November or so, we proposed something. And I was part of one of those groups, and we proposed the idea of what later on came to be known as impacting research, innovation, and technology. And I said, and our premise was exactly what I said in the morning. We are institutes of technology. How many technologies have we created for which we can take pride of? which has made a difference to our lives of millions in the country. What it takes to create such translation. So all of us do research because today nobody can survive without doing research in an institution like IIT. What do you do with that research output? Of course, we should continue to publish in the topmost journal because that's the certificate that you have done something new. In addition to that, the same eye, why can I not also be a PC ray? That I not only discover mercurious nitride, but also I see an application of that. Can I do that? If we can do that, then that will make a difference to the schools of IITs. The first slide that I showed you, the highest form of science and technology. Can we do that? So 2015 early, we proposed, ministry went through its usual practices of this SFC, EFC, this or that or something. 5th November 2015, imagine, I'm talking about almost 8 years ago. The Prime Minister, the President, the topmost leadership, political leadership of the country, comes to Rashtrapati Bhavan, Darbar Hall, where the ministries take oath, and announces the launch of this program, Imprint. Why? Because of single reason that we were talking about something which has never happened before. What are the reasons why? What were the unique features? We said we are going to discuss not one solar energy harvesting, not one nitrogen fixation, or one CO2 sequestration. We are talking about all possible engineering issues in front of the country, of all disciplines, concerning all IITs, all engineering institutions. So basically, entire 360-degree view. Number two, so first of all, entire engineering landscape. Number two, we are talking about all engineering institutions under the ministry and even beyond. So everybody would talk about. And number three, the most important reason, we are not talking about any new knowledge generation. We are only talking about making use of the knowledge already available. So we are not saying that no need of creation of new knowledge. We are saying there are knowledge documented or created by some of us. Can we make use of that with only one intention? Can we solve a defined problem? So what are the problems we are talking about? Here the problems were defined not from the entry side, not mechanical engineering problem, not electrical engineering problems, or not a problem of creation of a particular machine. Problems related to, or ambitions related to healthcare technology, problems related to sustainable habitat. So for buildings, roads or something, what are the challenges? What needs to be solved? So you're coming from the reverse side, from the user's side. If I'm a common man, I want a building which is supposed to be cheapest, most durable, very easy to fabricate, and so on and so forth. Similarly, if I'm looking at, I'm a defense minister. If I'm the defense minister, I want the country to have the best possible defense against airstrike, against ground attack, against sea route attack, or all kinds of possibilities. So, and so on and so on. So we divided the entire spectrum of engineering challenges into 10 specific domains. And these 10 specific domains had themes. So each domain would have 10 themes. 10 themes would have 10 specific topics, and 10 topics could be further defined to 10 titles and so on. So 10 raised to 4. And India being such a large and varied country, easily you have 100 variants of the same problem. Because as the locality changes, as the raw materials, the input changes, the problem also needs to be redefined. So 100 variants of each one of them. That makes it 10 raised to 6. So the Prime Minister, in the inauguration, we had to introduce. So we said, sir, we have come up with a 1 million problem. But nothing to worry about because we have billion minds. So the slogan was million challenges, billion minds. So with that premise we started. And why is it different than the grand challenges of US? 14 specific challenges. solve this, solve that, solve very specific pointed questions. That's how the science always progresses. But we argued that India is not in a position to pursue exactly those. I mean, when you talk of, say, solar harvesting, where is silicon? Where is silicon germanium? Where is my sensor? Where is my many other things that we require? Those countries, they are already at a level where they can afford to identify and pursue a very specific challenge, whereas we first have to raise the basic level. So we have to work in a different fashion. So then we try to synergize with all other various existing programs and so on and so forth. Just for an example, and each domain had to be chaired by one of the IITs. So energy was to be chaired by IIT Bombay. And these were the themes, specific themes that had to be addressed with an objective that we have to make country energy secure. For energy security, whatever needs to be done. So themes, then topics, titles, and so on and so forth. Challenge, approximately, let's say 350 gigawatt hour is the demand at a given point of time. And the mix is like 2/3 fossil fuel, almost. The remaining are all kind of different types of energy resources. You look at your fossil fuel reserve, you know these many years everything will be exhausted, so you have to come up with alternatives. How do you do that? And if you want to install solar panels all over, then all rooftops are covered. Then what happens to the panel after so many years? If you want to install the big windmills, where is so much of wind velocity? How does it change over a period of time? So multiple issues and so on. So they have to be all taken into account. And also one other thing, when we talk of energy, little do we understand that if I throw the number, you'll all probably be, those who are not aware will be surprised. If you produce 100 watt, 33 watt is wasted in transmission. So it's not just production alone. It's a transmission also which is equally important. Storage. Produce hydrogen. Where do you store hydrogen? So storage is more important than actually production of hydrogen. So this was now this is very important that in the morning I was talking about steel consumption, and I showed you a data that even after projected increase in steel consumption, India will still be 1/3 of the world average of steel consumption. So we are far away from being a developed nation until and unless we significantly improve our investment in infrastructure development and steel consumption. Similarly here, you can't do anything without energy. If you are trying to produce something, making a difference or change, then there has to be sufficient supply of energy and sustainable supply of energy. So in energy production level, we are, compared to the likes of China and US, almost 1/5 or even less. But even more worrisome is the fact that per capita electricity consumption wise, we are way too below than, say, the likes of China, US, Japan, Canada, Germany, and so on and so forth. So we have not only 350 or whatever gigawatt hour of demand. In addition to that, we have 1.4 billion people, very young people, and all of them want to grow. And the whole country is very keen to grow. And in order to grow, we need energy. But our per capita consumption as of today is so low. And if everybody demands, like you go abroad in Europe or in cold countries, you have heating arrangements and you have cooling arrangements and so on. These days, we are much better off compared to 50 years ago. I mean, at least I don't have to go back to that level. When I started my career, first 20 years, getting an air condition in my lab, leave alone office, was a dream. Today, everybody has an air conditioner in the office, at least in IT system. I mean, so such a difference has already been made. Still, our per capita consumption is so low. That means we are far away because you don't have to just go 100 kilometers away from this very spot. Look at the level of energy consumption. The guys depend on burning the woods, or maybe they get a bit of a gas cylinder supply once in a while or something. It's far too small. And traveling is mostly very inefficient traveling and so on. So imprint was launched. And 85 November, I think somewhere around 2015 November, so somewhere around 2016 middle, we started releasing funds. And just look at the numbers, 2,612 proposals received in 10 domains, 84 themes, 5217 individuals involved, nearly 200 institutions participated as PI or co-PI, 608 participating institutions. Cumulative figure of amount of money requested was 50 crore, 500 crore. And no, I'm sorry, 4,700. And then in the first phase, we accepted, in the first phase, that means screenings phase, 2,612 proposals, 924 in the second, 458 in the third level of scrutiny, and finally 259 were chosen. Eventually, only 140 or 150 were through because they couldn't get the partner from the industry. So, but the good thing was that all these so-called 50 or 140 were distributed all over the country. So that was a good thing that institutions participated from all over. Then we realized this model was not quite working. So within a year or two, the ministry wrote again another EFC and got a fresh bit of funding. Now the model is a little different. 50% will come from the Ministry of Education, but another 50% need not come from a partner ministry, because the line ministries have their own problems of, they say that we don't have a budget line or typical bureaucratic answers. So we said DST will fund the remaining 50%. That was imprint 2. I don't want to explain all those details, but the point is that November 2015 was launched and August 2019. So, but remember, the money flowed only in August or something. So within 3 years, we organized an event in IIT Delhi, and in front of the Honorable Minister, we showcased about 80 different models, prototypes, 80 different models. And some of them were already, they had already filed patent or were ready with the prototype or something. So for example, Nafkan showed something, HB1C detection with a point of care device. I mean, you don't have to go through the usual. HB1C is a very elaborate process. It is just by a prick of this thing, a blood test, immediately the result. Then Radhakant came out with artificial pancreas design and the cycling of that. So likewise, Suman came up with microfluidic device to detect some healthcare devices to detect hemoglobin and glucose and so on and so forth. So similarly, Rintia unfortunately is no more. Then Balaji came up with a high power laser source design. So many prototypes were developed and showcased. So that was the intention, that you continue to do your fundamental research, but if you see there's an opportunity, can you come up with at least a prototype, a 3-dimensional product, not just a publication. Now I'm going to switch gear and give you some examples from my CSR stint. Those of you who are not so much familiar, the younger ones, you should know CSR is a research organization in the country, in my opinion, which is truly the cradle in which Indian science grew, at least in the post-independence. 1942, when Dr. Bhatnagar created CSIR as the first DG, India was not even independent. And the first CSIR laboratory was National Physical Laboratory in Delhi, National Chemical Laboratory, Pune, second. Likewise, CGCRA was number 4 in the row. Why glass and ceramics? Again, because of a visionary. Meghnad Saha, borrowing from the experience of Second World War, convinced the government that India will require high quality glass, specialty glass. And in order to create glass, not only for just optical purpose, but today laser glass is important even for defense applications. So this laboratory was created, and I'll straight away go into one product, just 1 or 2 products of that. This yellow block that you are seeing is called lead glass. Tarapur is the place where atomic energy first showed the conversion of atomic energy into electricity. So it's called still the hot cell chamber of atomic energy. The windows of, it is in a radioactive environment, you cannot go and tighten the screw there. So you have to do from a very safe distance remotely. Even if you do remotely, you have to set up everything. And once you have set up everything, once you have set up and closed and made the reactor critical, for life you cannot approach there. Then how do you see where is my plutonium? How am I embedding in what? And if you make a mistake, if something falls off or get displaced, you cannot open the door, go inside, fix it, and come back. So you need a glass across which you can see very carefully, very easily and precisely. And the glass that is to be used by calculation of radiation, by the way, you or even school children know these days alpha, beta, gamma. So if you compare alpha, beta, you're not so much worried because they'll attenuate anyway within a very short distance of time through any medium, even in air. Gamma can penetrate even steel or any other solid objects, much thicker sections. So in order to prevent gamma from coming out of that chamber, you should use glass, and the most transparent glass is a borosilicate glass, which has a very high radiation of cross-section, absorption cross-section of radiation. But if you use only borosilicate glass, you require several meters, more than a meter. Now, imagine it has to be a monolith, fixed glass of, let's say, 2 meter or 1.5 meter thickness, to be produced in one single operation, which will have no difference in refractive index. Those who have worked with glass would definitely know I'm talking about something impossible. Because glass is highly viscous, not like metals, don't flow like water. And when you pour, when they solidify in layers, and it's amorphous. So if these layers actually do not carry the same viscosity, then the refractive index is going to vary layer to layer. So whatever, then you are not seeing direct transmission, you are seeing a refraction. So the object is not where you are seeing a projected image. You can't afford to do that. So you have to reduce the thickness. How do you reduce the thickness? This should have been a quiz to my young friends here. In order to reduce the thickness, what should you do? Increase the density. So the volume decreases. How would you increase the density? By adding higher atomic number elements. In this case, you dope not with boron, but with lead, very high atomic number. So you create a lead glass. Now this lead glass block is so corrosive that you can melt and solidify only in one type of crucible. And you'll be surprised that crucible is nothing but pure platinum. You know how expensive is platinum? So now you are melting and cooling in a platinum crucible of this big size, because glass is also fairly high density, so lead glass. And it has to have the mechanical property. You cannot afford to puncture it, so you have to have backup and then platinum crucible and so on. So if the project costs 100 crore, 75 crore would be only the platinum sheet. How much thickness? 1 or 2 millimeter, because I can't afford more than that. Who will fabricate pure platinum? By the way, platinum is FCC, but still not very ductile. It's a very hard metal too, actually, because of very high melting temperature. So now you realize what is technology. You know very well that I need a glass which should have this density and this refractive index. You have proven the Fresnel's law, and you have shown that if you do this, do that, and you have a nice window. How do you create that window? Now, when you try to create that window, then you face the heat. What are the difficulties? So you have to create a crucible. You have to create a separate design for that. You have to, if the crucible punctures, you have to have the welding arrangement of pure platinum, then various other things. So this project was started in 1960s. It took us 40 years or 50 years to deliver the last consignment to the atomic energy. And the atomic energy people were very happy, and I was very fortunate because I was that time the director of the lab, and they heavily complimented us. 20-ton supply took us 50 years to complete. Now the question is that somebody may say that, a typical trader would say that, I could buy it from Russia or Germany, from SHOT or USA, and why should I spend so much time and money on you, pay so many salaries and so on? Here comes the question of self-reliance. If you don't do it, of course, shot glass will provide you, or other Corning or somebody else will provide you. And at the very moment when their political leadership decides, no, India is getting too smart, so you pull the plug, they'll stop the supply. Now what do? Your atomic energy establishment, you can't switch off. So the country has to invest for decades, if not centuries ahead. And it takes time to build that skill sets, that manpower, the trained manpower, that set up infrastructure, and have a long-term vision. If the country has decided to pursue atomic energy option, there's no other choice than to be self-reliant in all possible aspects of that. So here is one such example. What do you do with the spent fuel, uranium oxide? Residual radioactivity. You can't throw it in the open. You can't bury it underground because it will have residual radioactivity. So you can't even just pack it up with some metal pieces and throw elsewhere because still it will radiate gamma ray. So you have to embed in something which will not corrode. What will never corrode? An oxide, because it's already corroded. So you embed in silicate with very strong covalent bonding, replacing some of the silicon 4+ with uranium 4+, and bind it with covalent bonding, and melt and make it a glass block. Cover it up with steel blocks, very thick steel block. Even with the hardest possible, say 8-9 Richter scale earthquake, it may get deformed, but that metal piece will not break. And then you cover it up, push it way below your desert area in some remote places in concrete blocks. That's how you take care of your spent fuel. So these glass beads were created by CGCRI. Technology was proven, shown, and demonstrated. No taker. Because it doesn't fetch a lot of benefits, a lot of profits. Companies are not interested. So it took us quite a few years eventually to convince one of the companies, Mumbai-based company, who finally came forward, took the technology and started supplying to atomic energy. 3 separate technologies were developed, transferred to the company. Still, we are nowhere in the global scene in terms of competing with the competitors. So what are they? I mean, we all use this cell phone, which is supported by the optical fiber network. We need a booster, we need an amplifier. That was developed, designed and developed in CGCRI. Fiber Bragg grating, those who are in, I mean, there are multiple examples. Let me fast forward. Supercontinuum source with a very large bandwidth of wavelengths and so on. Another very interesting example. Artificial hip joint, knee joint, finger joint, maxillofacial joints, and all kinds of things. Prosthetic implants, right? Now, look at the numbers. Device in 2011 used to cost 1.5 lakhs a piece, a pair. This CGCRI implement actually costed only 25,000. Technology was developed, transferred, demonstrated. 100 patients benefited from these implants all over the country. And a very famous surgeon, K.H. Sancheti from Pune, did many of these operations. And he himself certified that it is even better than the imported stuff. Still, it was very difficult, and I know what has finally happened. It's practically impossible to convince because the way things are marketed, and you see, this is where the technology is different than engineering and science. The way the foreign products are marketed can easily convince you and I And we'll be ready to pay 1.5 lakh. That general mentality is, no, after all, it's the question of my own knee. I don't mind paying another 1 lakh rupees or so, I'll better do that. Nobody actually is talking about the quality of the product. So in order to build that reliability, you have to play the game. That's technology. It doesn't require always an atomic energy or lead glass or very, very exotic things. The whitewares or certain clay products are made out of what is known as Ukrainian clay. I'll again throw just numbers, then you'll realize. Just the last part. For certain intervention, a product which earlier used to require 20% of Ukrainian clay imported from Ukraine, now got reduced to 1%, so practically negligent. As a result of which, the total consumption got drastically reduced of such imported stuff, and the number of units which used to be 14 who produce such products and sell rose from 14 to 64 just in about 4 or 5 years. So instead of 14, now 64 companies are selling that product. Each one of them now is earning a profit margin higher by 3.5 crore per company. So imagine the economic benefit to that set of manufacturers and the country as a whole. How is that possible? A very simple intervention. Somebody, not even a scientist, a technical staff in the lab showed that some local clay, which used to contain a lot of iron oxide, could be leached and made iron oxide free, because iron, when you melt at high temperature iron oxide, it gives a reddish tint, and that ruins the whiteware or the white luster of the product. So he showed that could be leached out and the product could be as white or as bright as the Ukrainian clay. So that makes such a huge difference. So technology does not necessarily mean always very large investment, very complex, very sophisticated, nothing of that sort. Sometimes it could be very simple design change. Maybe a curvature of this to that, or maybe a length of this to that, or something like that. That can make a huge difference. But that insight is very, very important. Now, before I end, I want to just bring your attention to a very important fact. This is India. It's a very complex, not complex, it's a very interesting milieu where we have all kinds of faces, all kinds of, you travel every 200 kilometers, the food habit, complexion, the general human face features, the religious practices or rituals, the festivals, the language, the customs, food habits, everything changes. Everything changes. So in order to come up with specific solutions, we have to understand again where do we stand, what is the ground reality. So I have two sets of information to share with you. Historically, we are one of the oldest civilizations. That's what we have been discussing since morning. And used to be richest until 1700. Until 18th century, we have to be one of the richest. We used to be one of the richest. So several other things. I mean, large GDP, fifth in terms of nominal, third in terms of PPP mode. We can successfully launch lunar and Mars missions. We can launch satellite, 36 in one single launch. The ISRO chairman explained to us the other day that 36 satellites as garlands, were launched in a single launch by one single rocket. So a lot of countries come to India. India actually makes a lot of money from these capability. So these are, and now look at the industrial side. We are number one in drug and pharma industry, number two in steel, cement, coal, telecom, food and agriculture, number three in electricity, construction, real estate, number four in automobile production, and ninth in terms of aviation market, such large market. And yet look at the flip side, the diversity in terms of 37 states and territories, 22 languages, 8 main religions, the per capita income being low, and so on and so forth. So there are multiple challenges, and many of them are related to the energy, defense, water, and education, and that's why you need engineering. So this is the puzzle I was talking about in the morning, that capita consumption, in India, we have something called the denominator problem, you know. For example, in metallurgical departments, everybody will say that I have an electron, very high-end electron microscope. How many users? 50. Time per user, not even 1 hour per week. You can't do very good research with that. So we have facilities, we have resources, but the total number of users is so large, that the population is so large, we have a problem. So here what I'm trying to say is that the Indian economy is supported largely by the service sector and IT sector and so on. This is not a very good sign. We have to reverse, where instead of 59% coming from services, it should be 50% coming from manufacturing, so that there's a shelf value of time. This is also an interesting figure, the Human Development Index as a function of per capita power consumption. So this is a relationship you see. India is way below, somewhere around 50%, 0.5, compared to the developed nations where they are. So we have to bridge this gap. So that means while we try to improve the quality of life, we should also be able to improve the energy consumption per capita. That means it should be more affordable, and not by burning coal, but by using renewable resources. The expenditure, one of the puzzles here is that this part is fine, the left part is fine, that India's expenditure in the research is not so low as we tend to believe at times. But India's expenditure out of its GDP is way too low compared to the developed nations. It's just about less than 1%, 0.8 or even less. Whereas if you go to Korea, 4%. Go to Scandinavian countries, easily between 2 and 3%. So there, India needs to spend a lot. And then this is something I would rather not discuss. It's a bit of a controversial slide, but I honestly believe that our evaluation system needs an overhaul. If we continue to only count the number of publications, citations, and H-index, we'll never be promoting translational research. We are doing actually a disservice there. National education policy is all well known to you. I don't need to talk about but what is new in it? It is now talking about an interdisciplinary, approach of interdisciplinary education, which was not possible until now. So somebody starting with a medicine degree can end up with a engineering or philosophy degree, or somebody with philosophy can eventually end up as an engineer. It is talking about credit bank, it is talking about, there are very many good interventions, but not all of them are very easy to implement. And this is where we have to come up with some tangible solutions. So I think that's all. I'll just stop here saying that what I mean by the synergy, I mean science is pursuing the truth relentlessly, regardless of its necessity or immediate scope of application. Science provides clues, if not answers. Science extends as far as we can imagine, and science never fails, but the scientists can. Engineering, on the other hand, is all about enabling and providing solutions, borrowing from the fundamentals of science. And technology is the last mile for societal benefit based on scientific discovery and engineering interventions and innovations. So we need to ensure that science, engineering, technology complement each other. There's a reversible sign. And if India has one unique resource and strength that this entire world envies, that certainly is our demographic dividend, the youth. So we actually have to leverage the power of engineering so that it can ensure self-reliance and hence self-esteem. Someday in the future, we should be able to not only claim, but actually prove that we are at par with any other nation in the world. And for that, this is the dividend. So, thank you very much. And I think I should stop here. I have taken, as usual, longer. Okay.
So thank you very much. So we can take a couple of questions, quick questions maybe from the students.
I think they are all jaded.
From the students, couple of quick questions. Doesn't look like. Anyway, we are late, I guess. So, yeah, so that is open anyway. So from the Dhara participants.
I see, yeah, yes. Please be seated.
Yes. So actually, you mentioned that the percentage of amount of money spent in research in India is less, like if you measure the percentage of GDP. Is there any particular reason for that, or like?
No, actually, you have to understand that when you look at the actual figure, you tend to believe it is very, very low, like 0.8 or even less. But actually, the government argues that there are many indirect ways government supports um, research. Indirect ways in the sense, for example, this kind of a model you'll not see in developed nations where the land, the building, the entire infrastructure, salaries and everything are paid by the government. So there are multiple institutions, multiple infrastructures that the government maintains, which are not immediately seen within the list of investments under so-called R&D. But government never also denies that it should improve and it would like to improve the level of funding. But fact remains that yes, even if government is spending indirectly, but if we have to compete with the rest of the world, there's no other go. We have to. But I mean, since I have the opportunity of serving in many committees, I can also tell you, let's say today government is spending 100 rupees on research. Tomorrow, right tomorrow, government declares we'll spend 200 rupees for research. The quality of the project proposals will not be able to satisfy the reviewers. In other words, we have to improve our capacity building before we actually can utilize that amount of funding. So it has to go in stages.
Okay, sir. Thank you, sir.
Any other question?
Okay, I think Professor Balal is getting late, so I think we should stop here.
Yeah, looks like no more question. Anyway, we have the platform open till tomorrow to interact with you. So we can conclude the session here with a big thanks to Professor Manna for the exciting lecture.
Sir. So thank you, sir. Thank you for delivering, sir, such a important topic. And that is really mind-blowing and enlightening also. We all are, the entire IIT Indore and is thankful to you. May I now request just 2 minutes, as a token of appreciation, I would request our convener to present a memento to Professor Manna. Sir, please. Though we are running short of time, but without acknowledging such a person of high stature, it would be incomplete. Thank you. Thank you, sir. Thank you for being with us. And thank you all the participants, all the students, all the distinguished guests over here who could find out time to listen to the important lecture. Thank you. All the participants may please be seated at the Gargi Seminar Hall, just adjacent to this, where your program started in the morning. Please be seated in Gargi Seminar Hall. Yeah, this is Mathur Seminar Hall. Just adjacent to this, we have Gargi Seminar Hall, where your program started in the morning. All of you can join for a cup of tea also arranged outside. Just take 5 minutes break, take tea, and be seated in Gargi Seminar Hall.
हेलो हेलो कृष्णा देख
नहीं आ रहा।
हेलो हेलो माइक टेस्ट
रॉड से ले ले फिर। ठीक। हैं? कौन से नशे कर रही है? तुम की आज कॉपी हो गया? तापस, ये एक टाइल से कॉपी हो गया? तो इसमें एक ही कार्ड की तो फॉर्मेट कर दो ना। हाँ, तो इसमें डाला है ना